Chemistry theory. This is part 2 of the EQ 3.2 section, Bronsted-Lowry acids and bases. So now we looked at what happens in terms of H plus donating or accepting, resulting in an acid or base formation. Let's look at acid-base pairs. In any acid-base equilibrium, both the forward, and of course I didn't mention it before, but there is a reverse reactions that could happen here as well. So there's a reverse reaction of it, which also involves a transfer of an H plus. So for example, if we look at this, now HX of course doesn't exist. X is just a hypothetical negative ion that's combined with HX. In the forward reaction, if we take a look, HX donates an H to become donates an H plus ion to H2O, because if we look here, HX is closely related to X. Okay, we can see that from HX, to go from HX to X, it lost an H, or donated an H. So anything that donates, we said, was a Bl acid, a Bronsted-Lowry acid. And then H2O is closely related to H3O. It differs by a single hydrogen. We can see that it accepted the H plus, and when you accept something, you're the Bl base, or the Bronsted-Lowry base. So in the forward reaction, HX donates the H to the H2O, so this H is going to go to here. So HX becomes X, H2O becomes H3O. Therefore, HX is the Bronsted-Lowry acid, and H2O is the Bronsted-Lowry base. But if we look at what's going on in reverse, if I go backwards, H3O becomes H2O. It's donating an H. It's losing an H from going from left to right. So that is referred to as an acid, right? Because something that donates an H, loses an H is an acid. And of course, X, to become HX, accepted an H, and anything that accepts an H is referred to as a base. So when the HX donates an H plus ion, etc., likewise H2O acts as a base, etc. An acid and a base such as HX and X that differ only in the presence or in absence of an H plus. No, we've kind of done that, because in pairing these up, they differ by a single H. HX and X differ by a single H. H2O and H3O, they differ by a single H. So those are called conjugate acid-base pairs. Conjugate, the word meaning joined together as a pair. Every acid has a conjugate base formed by the removing of an H plus. So if I look over here, HX was a Bronsted-Lowry acid, and it became X, which is going to be referred to as conjugate, I'll just put CONJ, conjugate base, because going backwards, it gains. So you'll have an acid-base pair. What is a Bronsted-Lowry acid on one side is a conjugate base on the other. And likewise, a Bronsted-Lowry base is paired up with a conjugate acid. In reverse, it's losing an H. You always have that, acid-base pairs. Acid-base, acid-base. So for example, OH is the conjugate base of H2O, and X is the conjugate base of H plus, or sorry, of HX. For every base has a conjugate acid by the addition of H plus. Okay? In any acid-base reaction, we can identify two sets of acid-base pairs. For example, consider this. So if we look over here, we can see that HNO2 becomes NO2. So there's a pair, right? They differ by a single H. So HNO2 became NO2, so we know that this H got lost. And then H2O becomes H3O. So the actual H transfer was like this. And then comparing before and after, we can see what happens. Acid gives it up, base receives. Then if we go backwards, NO2 negative to become HNO2, it needs to accept an H, therefore it's a base. Going backwards here, H3O to become H2O, released an H, so it's behaving like an acid. So you'll always have a conjugate acid-base pair. If we look at the next page, we can see another example here. NH3 becomes NH4. So it makes sense to pair up these two together and not these two, because these differ by just more than a single H. These differ by an H, these differ by an H. So they are the conjugate acid-base pairs. So that's what you have to do first, and then see what's happening. NH3 to become NH4, we added an H, or I like to use the words, we accepted an H, whereas H2O to become OH, we donated an H. Ooh, that turned out kind of weird. So there we have that. And then NH4 to become NH3, it's releasing an H, donating an H, so it behaves like an acid. OH to become H2O, it's receiving an H, so it's behaving like a base. All right, so there's 4 examples here. You may want to pause the video and just try 1 or 2. But what I'll do is I'll go through A right now, and then you can pause it and see if you can do the rest, then tune back into the video to see how you did. So identify the Bronsted-Lowry acid, the Bronsted-Lowry base, the conjugate acid, and conjugate base in each of the following. So first of all, you have to identify the conjugate acid-base pairs. So HClO4, you can see is related to ClO4 negative. It doesn't make sense to pair these. They differ by more than a single H. These differ by an H. So if we go from here to here, HClO4 to become ClO4 negative, you can see that we lost an H when going from left to right. So we can say donated an H plus, and of course something that's donating is an acid. And then going from here, H2O to become H3O, we accepted an H plus, and anything that accepts an H is a Bronsted-Lowry base. Okay, then going backwards, ClO4 negative to become HCO, it accepts. Therefore, this is going to be the conjugate base. And H3O, to go backwards and become H2O, it donated an H. And anything that donates an H is an acid. So this is the paired up acid. And notice here, a Bronsted-Lowry acid is paired up with a conjugate base, and a Bronsted-Lowry base is paired up with a conjugate acid. So remember, you always have an acid-base pairs. Acid-base pairs. So you always have that happening. All right. So you may want to pause the video, try the remaining 3. Otherwise, I'm going to continue on and work them. So Cn is related to HCN. It accepts an H. So we know that anything that accepts is a base. And we know darn well that this is going to be an acid in reverse. Conjugate HCN to become Cn, it lost an H. I should go back here and just show what happened to this H plus, so that's actually what happened there. Then of course vice versa, that's what happens. So then over here, H2O to become H3O, so we know that it donated an H plus, and anything that donates is a Bronsted-Lowry acid. And we know that it's going to be paired up with a base. Conjugate, oops, not sure why I did a line there. OH to become H2O, it had received an H, so it's behaving like a base. Over here, H2S is closely related to HS if we donate an H plus. So anything that donates, we can see that this is what happened here. The H went from here to here. So this is a Bronsted-Lowry acid, which means this has to be the conjugate base. HS to become H2S, yes, it received an H when going from right to left. Then of course we know what's going to happen here. H2O to become H3O, it received, accept an H plus. I'll try to make this a little bit bigger next time. So H2O to become H3O, it behaved like a base by accepting an H plus. And then vice versa, H3O to become H2O, It's behaving like an acid. There we go. Last one here, SO4 2 negative to become HSO4. You can see we accepted an H plus, whereas here, to go from H2O to become OH, we lost an H, or donated an H plus. So anything that accepts an H is a base, and it's always going to be paired up with an acid, conjugate acid, because we can see HSO4 becomes SO4, it loses an H from left to right. H2O to become OH, we can see that it lost an H, so it's the Bl acid, and that is, of course, is going to be paired up with a conjugate base, because OH becomes H2O. It receives an H. All right, so that's how you do that. So Bronsted-Lowry acid bases paired up with conjugate acids and bases. The key thing here is to pair up the conjugate acid base pairs, those species that differ by a single hydrogen. All right, you should be able to do the assignment, and we'll see you again.